So I'm going to give a talk about quantum algorithms, and since this is a workshop focused on crypto and lattices, I'm trying to have a talk on quantum algorithms, crypto and lattices together. So some parts I'll talk about just quantum algorithms, or I might talk about the connection between these two in some instances, or I might talk about how the lattices are used in some quantum algorithms. And, well, hopefully someday in the future, maybe we could use these words in a different sentence, like quantum algorithms for breaking crypto based on lattices. But that's still, of course, an open problem. But I'll tell you how these are related currently. So here's an outline of the talk. I'm going to start by talking about the hidden subgroup problem. I'll spend some time giving a lot of examples of this. This is a problem that models most exponential speedups that we have for quantum computing. I'll mention a few other problems that are not hidden subgroup problems to show you something else. And then I'll give you some idea how the quantum algorithms can solve the HSP. Solve these problems so that they get reduced to it. And at the end, I'll give two approaches that don't work, that we've been trying for a long time, but we can't seem to make work. And things will get progressively sketchier as I go along. So hopefully we'll start okay there. Okay, so I'm going to start by defining the hidden subgroup problem and giving lots of examples. I'll also I'll tell you why solving the hidden subgroup problem is different than, say, the lattice problems, even though you can see lattices sitting there. Okay. Okay, so we have this hidden subgroup problem. So the setup is there's a known group, G, and a set S. And you know whatever you want to know about G, and you have efficient operations for it, like the group operation, identity test, whatever you want. And in the problem, you're given a function, f, from the group to the set, and it hides a subgroup in the following way. So the conditions are that the function is constant on cosets of an unknown subgroup H, in the group. And the second thing is the function takes distinct values on distinct cosets. And the goal is to find H. Okay. So what this means is, in terms of running time, is we want to find a set of generators for H in time poly of log G. Okay, so this means generators. So find a set of generators of H time poly log G. Okay. So you can think about having your group. So if you have your group elements here, there's this unknown subgroup you're trying to find. You have the cosets of that subgroup. And if you evaluate the function, so say you have all the elements that are in the subgroup, these all evaluate to whatever f of 0 is, say, if 0 is your identity. The next coset evaluates to whatever, pick some coset representative G, whatever f of G is, and these values are different, okay? And so on. So let's start with a simple example. So here's the first example of a hidden subgroup problem. Let's consider the group G being Z2 to the n. So this problem was studied by Dan Simon. So Simon's goal was to show that quantum algorithms can't do anything, and he came up with this problem. It turned out to be the start of a lot of good work. Okay, so let's see how hard this is. So if you want to see that this is a hard problem, just consider an order 2 subgroup here. So if the size of H is 2, then F ends up being a 2-to-1 function. And to solve the problem, you'd have to find a collision. And you just have an oracle, so you can't do anything other than query. So this is a hard case classically. So the next example, let me just say where you can see lattices already. Let's take the group to be z to the n, okay? And then the subgroup H can be a lattice. So here's one place where lattices come up, and you can see the problem is different than, so the problems we've been talking about are like, given a basis of a lattice, compute a short vector. This problem is different. This problem is, given a function that hides a lattice, compute a basis for the lattice. Okay. So, compute a basis. So if this is a lattice L, then you want to compute a basis for L. All right, so before I get through some more examples, let me just say what's known about the quantum algorithms for solving this problem. So for most abelian groups, there are efficient quantum algorithms. So it's sort of just, so for example, Z, you can solve it when the group is Z or Z to the n. You can solve it for R, the reals, constant number of copies of the reals, finite groups. And when the group is non-abelian, we know very little about it. I'll say a little bit more about that for two groups. So there are algorithms for some solvable groups. There's an algorithm for a certain semi-direct product that looks like this for P of fixed prime. So there are some special cases we can solve, but not the ones we'd like to solve yet. And I'll show you two examples of reductions of problems to the non-abelian case. Or at least I'll say what the problems are.
When you say you can solve it efficiently?
Yeah, efficiently.
And for finite group, if the size of the finite could be exponential in the security parameter, you can still solve it all on this?
Yeah, you should think of the group as being exponential size. So we're working in size polylog G. So just you can think of the input size as like how many bits does it take to write down a group element. If you were allowed exponential time, then you could just, or if you were allowed time the size of the group, then you could just brute force query through here. But that's not allowed. Okay, let me go through some more examples here to show you. So the next example will be for factoring. So in this case, we'll let the group be the integers. And this is Shor's algorithm, piece of it. So here you want to factor an integer. So let's suppose you're given an integer n, and you'd like to factor it. So there's this fact that factoring n reduces to computing the order of a random element mod n. Right? So the hidden subgroup problem is going to be just finding that order. So factoring reduces to computing order of a random element mod n. So if we can compute the order of an element mod n, then we can factor. Okay, so we can define a hidden subgroup problem to do this. So let's say we're given some element x mod n. We'd like to know the order. What we can do, we want to define a function that has these properties where the hidden subgroup reveals the order. So let's define a function f from the integers to integers mod n. And we'll just take and map I to x to the I mod n. Okay, and this is an HSP instance. So in this case, the subgroup is going to be, what if the order is R? It's going to be multiples of R. So this is the order of x mod n. And so you can maybe think about what the function looks like when you plot it. I mean, so you have this function at 0, it's x to the 0, so you get 1, and then you have x, whatever x is, and then you have x squared, which is maybe some other value. Say it has order, let's say it already repeats here, and then here you'd have 1 again, and then x again. So this is evaluated at 1, 2, 3, 4, 5. Right, so you can see the subgroup is just the multiples of the order. And then you have these cosets. So here on this coset, it takes the value x, and on this value, it takes whatever value x squared is, mod n, and so on. Usually the period is much bigger. If the period was this small, you could just, of course, query it yourself. But if the period is exponentially large, you can't just query that classically. Okay, so this is constant on cosets and distinct on different cosets. Any more questions on this example? Yeah. I mean, you can define it. Yeah. There are details. I mean, yeah, you have to, yeah. That's the way I'm doing it right here. Yeah. That's right. That's right. If you wanted to do it on a finite group, which is where the quantum algorithm is much easier to analyze, then your group order would have, like, the order of the element would have to divide the group order, but you can't know the group order without, you'd already be able to factor. But what you can do is you can pick a different finite group that's a large enough size, and it'll sort of approximate what you want. Other questions? Okay, so here's the example for discrete log. If we take zp minus 1 cross zp minus 1, so this is a finite group, then you can imagine if you're given a generator, some element g to the r prime p, and we want to define an HSP instance, so we're trying to figure out what r is. You can define f of ij to map to g. Well, I'll write it in terms of how you would compute it, g to the r to the minus j. So you have g to the r, and so you can compute this whole product, which gives you g to the I minus rj, working mod p here. Right. So in this case, the subgroup would be generated by pairs J times R. Well, it's not generated by it, is this set. And so if you could solve the hidden subgroup problem, you know, you could say, here's my function, you'd get back a generator for the subgroup, and if J is relatively prime to P minus 1, then you can compute R from it. So you could, you know, we're thinking about sampling, or actually, if you have a basis, it's good enough. So if we let G be Z to the n, then there are a few things we can do. One is decomposing finite abelian groups. So if you want to decompose finite abelian groups, suppose you're given generators G1 up to GK, and you're given you're able to do the operation, and you want to find relations. Then you can just define F to map, well, this K is that N, to just compute this product G1 to the I1 up to GK to the IK. And this will be a hidden subgroup problem instance. The hidden subgroup problem in this case will just be, the hidden subgroup in this case will just be the lattice of relations, right? So you get the set of tuples such that, oh, that's not great notation, equals the identity. So you'd be given a basis for that lattice. So these have all been pretty simple reductions so far, and there are more complicated reductions for some problems. So one example is counting points on smooth projective curves of genus G. This was shown by Kieran Kedlaya.
Would it be I1 to IN?
K is N here. Yeah, K is N. Sorry. So count number of points on smooth projective curve of genus G. And other problems just related to function fields also. So there are problems in function fields that are the analog of the problems that come from number fields, like computing the unit group, computing the ideal class group, computing the principal ideal problem. And you can solve those problems here also for arbitrary degree function fields. And that was shown by myself and Kirsten Eisentrager. So these are some examples of problems that reduce to that case. So there the reductions are pretty complicated compared to the ones I've shown you. Okay. So let me show you two things we cannot solve, but where we have reductions, two non-abelian groups. So the first one is symmetric group with permutations of n elements. And in this case, there's a reduction from graph isomorphism to the problem. Well, let's say I'll write it as graph automorphism, but you can do either one. So here you're given some graph. And you want to figure out what the automorphisms are. You can just define f of a permutation to be the permutation applied to the graph. And then the hidden subgroup in this case is just going to be the automorphism group of the graph. So this we don't have a quantum algorithm for. but it still is a nice example of the hidden subgroup problem. And the last example I'll show you is, well, no, second to last example I'll show you is for the dihedral group. So the dihedral group is semi-direct product of a cyclic group in Z2. And in this case, well, okay, it's related to the unique shortest vector problem. You have a question?
I have a question. So you say that the function has different values in different cosets.
Yeah.
But do you have to be able to tell the different values? I mean, if the value of the function is a graph, then to tell whether the values are distinct, you have to tell whether the graphs are distinct.
Oh, well, yeah, this hides some details. You have a way to write it down. So you can think of having, you want the set of edges to be the same. So if you apply an automorphism, the edge set will come out the same. Right, yeah. Okay, so this one is related to the unique shortest vector problem. I'll try and say a little bit more about it later. And by related to it, I mean, if you could solve the hidden subgroup problem over this, maybe you'd solve the unique shortest vector problem. Or, okay, that's what I can say without actually showing you how it works. If I give you an idea how it works, you'll see what the actual relationship is. Now, here, there's more known about the dihedral group. So these two groups actually behave very differently in terms of the type of the quantum algorithm that we usually apply. So first of all, there's a sub-exponential time quantum algorithm by Gray-Kuperberg, but it doesn't work, and you can't use it to get a sub-exponential time for the lattice problem, unfortunately, as far as we can tell. And yeah, can I say more later? Yeah. The problem is it requires a little bit of quantum, and I'll do that a little bit later. Yeah. And one of the differences here is we have some negative evidence for the symmetric group that our current techniques won't work. So we do Fourier transforms over these coset states, and the parameter we need in that theorem to show that that technique's not going to work is that the symmetric group has really large irreducible representations. And in the dihedral group, the representations are mostly just 2 by 2, so it seems different. These two seem very different, and you have this giant cyclic group sitting in there, and we know how to solve the cyclic group. And there are all these things about the dihedral group that make it seem like maybe we can solve it, but we haven't been able to yet. There's also information theoretic results that are stronger for this case than this case when we create the quantum states. So I'll try and say more about that later. Other questions? Okay, so I want to talk about, the last example will be powers of R, but before I do that, let me show you a couple of other problems. If I can find my notes here. A couple of problems that are not hidden subgroup problems, just to show you something different. Show you something related to crypto. Okay. So the first problem is the shifted Legendre symbol problem. So in this case, you're given a function, f, and it evaluates to, so if you evaluate it at x, it evaluates to the Legendre symbol of x plus s, working mod p. Okay, and the goal is to find s, so find this shift. So this is a lot different than the hidden subgroup problem. For example, this function basically takes two values, just 1 and minus 1, right? It tells you if the number is a square or not, mod p. So the structure is very different than that. But there's a polynomial time, we found a polynomial time quantum algorithm with this. This is with Wim van Dam and Lawrence Ip. And we did this back before Craig figured out how to get fully homomorphic encryption. But at the time, we read this paper by Bonnet and Lipton where they looked at fully homomorphic encryption and said, suppose you had fully homomorphic encryption. And they made a couple of assumptions and then showed that there's a sub-exponential algorithm to solve it. And it's related to this problem, so I'll show you. So in this paper, they assumed one of the big assumptions was that you can test whether or not you have an encryption of 0. So let's say we have, I'll just write down 0 tests. So you can test if you have an encryption of 0, and then they had a couple of other assumptions. I don't remember what they were, but that's the only one we need for this. Okay, so with this assumption, we can actually break such a system using the algorithm for the shifted Legendre symbol problem. And I'll show you how to do that. Okay, so in this case, let's suppose we're given an encryption of S. And now we can we can create encrypted values of the product of its ciphertext, and we can add. So to create, what do you mean? Mm-hmm. It's working mod P. It's just you only have in the field, yeah. So we just want to compute something that looks like this. So we can take our value x, and we can encrypt x. We can add it to S. So this is the idea before we actually do the operation. And then we can raise it to p minus 1 over 2. So here we'll use the addition operation for the homomorphic encryption, and here we'll use the multiplication operation. And so what you end up getting is the encrypted value of x plus s with p minus 1 over 2, which is the Legendre symbol. Okay. So now we have this encrypted version of 1 or minus 1, and we just need to know which one that is. So then the next step would be to take that and just subtract 1 from it. Test if this is 0. And if it is, then you know that the Legendre symbol evaluates to 1, otherwise it evaluates to minus 1. And then you could use this in the quantum algorithm and compute the value of S. So there's one connection to crypto. Now, one of the reviewers of the paper pointed out that you can also use Shor's algorithm to undo this, but okay. I still think this is a nice example. So that's one problem. It's not a hidden subgroup problem. Breaking the crypto system was not the point of the paper. It was actually the algorithm. Yeah.
One question. So Legendre symbol is an example of coefficients of the GL1 function. Can you do the same for coefficients of GL2 functions? So does there exist a quantum algorithm? So, for example, translating to elliptic curves, where you have elliptic curve and you had sequence coefficients E of n and A of n, and another sequence of coefficients that were A of n plus s.
I don't know. I'll have to ask you what the objects are. I can't even repeat the question in that case. But the points come from an elliptic curve. And so maybe I'll ask you afterwards about that. One generalization is to bent functions. Bent functions. So I'm not going to define it. I'll just tell you. This was shown by Martin Rotteler. Okay, whatever the definition of a bent function is. So it's a much wider class. It's a class of Boolean functions that have certain properties. You can solve that case. Another problem deals with finding the radius of a sphere. So in this case, you're given a superposition over a sphere. So a sphere S, and it's offset by some value k, and you want to find the radius. by Childs, Schulman, and Vazirani. They gave a quantum algorithm to find the radius of a sphere in this case. And one last example I'll give for now is just that there's been some work lately on reconstructing polynomials. So you can evaluate a polynomial and get back the, think of an encrypted value of the function value. And you want to figure out what the polynomial is. And for some restricted cases, people have been able to do that. Okay. All right, so those are the examples of some other problems. Now I want to go back to the hidden subgroup problem and talk a little bit about what happens when you go to the reals. And then we start running into number fields. Problems over number fields. Okay, so this will be the last example here. So let's start with R. Consider R and constant number of copies of R or high degree. So the problem here started with Pell's equation. So just to make this a little bit concrete, this is going to get sketchy because I can't cover everything or say everything detailed enough right now, but I'll just give you an idea of what happens. So you're given a positive non-square integer, and you have the equation x squared minus dy squared equals 1. And you want to find integer solutions x and y to this equation. And it's known that there's a fundamental solution, so there's some solution x naught, y naught. So we have this thing called a fundamental solution. And the fundamental solution has the property that you can compute all solutions from that one. So all solutions can be computed by looking at the fundamental solution, the x naught plus square root dy naught, and then raising it to the nth power. So as you take different powers of n, you get a number of the same form, and then you can read off what the nth xn and yn is from that. Okay, now in general, these numbers are too big to write down. They can have, we want to be polynomial in log d in this case, and these can have doubly exponentially exponentially many bits, say, to write down as far as we know. And so instead, what you do is you work with the log of the numbers. So let's define R, which is the regulator, to be the log of the fundamental solution written as x naught plus square root dy naught. Okay, so if we work in this embedding, then the solutions become integer multiples of this instead of powers. It's integer multiples. And then we can think about trying to define a hidden subgroup problem where the period is R. So here, solutions are multiples of R. Okay, so let me just give you let me just say something about how you can get a function like this. So we'll define a function f from the reals to ideals of the ring of integers in general in the number field. This applies also to the general number field case. And we'll take a vector t and we'll map it to e to the t times o. Okay, so this is some notation for something. So this is an ideal. It's a principal ideal. Is it a principal ideal? No, it's an ideal. I don't know if it's principal, but the way the map works is it does sort of exponential stretching in one coordinate and exponential squeezing in the other coordinate. So you take pointwise product. So so e to the t acts on all the elements in O in the following way. So if we embed O, say, as alpha alpha bar, you do pointwise multiplication. So you get e to the t alpha, e to the minus t alpha bar. And That's what the map looks like in 2 dimensions. So one thing you can see is that this map preserves the algebraic norm, right? If you multiply the coordinates together, then you get the same value. So when you embed your number field, say you have the 1, 1 point and 2, 2, and so on, if we look at how this map works as we vary t, it moves things along the norm lines. So it would take all your points in O and it would start moving them along these lines. So it does the exponential stretch in one direction and the exponential squeeze in the other direction. Okay. Now, the reason why this is going to be periodic is because if t is like log of a unit, then e to the t is a unit, and the unit times O is O. So you're going to get O back. Right, so just in general, if epsilon is a unit, well, it's if and only if, but and so when you would evaluate this function, you have e to the ln of the unit. That would be epsilon times O, and that would be O. So in this special case over here, where we just had R, you can imagine also taking multiples of it. So suppose we had e to the k times R times O, then you'd get e to the, oh, that's log R, not R. Oh, no, it's R. E to the k R times O is e to the R times O to the k. And then e to the R was the unit, so we get back O to the k. So you get this periodicity property, the multiples of R. Well, that's yeah, I haven't said really what it is. Yeah, it's lattices. Yeah, it is. It's the ideals. Somehow, some representation of the ideals. Say that again? Yes, yes, yes. Yes, yeah. Lattices, but yeah. Yeah, generalized ideals, I guess. The trivial ideals. Well, this was only if this is a unit. You mean because of this? Or? No, I mean, so that you're not going to get O back until this guy gets all the way out to the next unit on the line.
Well, but then if you're in the middle, it's not an ideal of O, but points that are transcendental.
Yeah, can we say generalized ideal and be okay with it, or round off and then it is an ideal, right? What's the same? No, they're not the same. There are some morphics. They're different. All right. So in the constant degree case, if you have a constant degree number field and you do this kind of setup, then we have a quantum algorithm for solving that. And so in these cases, it's a big problem, like how do you actually represent these ideals? And I'll just say that the hidden subgroup is the log embedding of the units. And then so that's a lattice. You're trying to find a basis for that lattice. So when you compute the unit group, that's the goal. Find a basis for that. And the question is, how do you represent these lattices, these ideals? And in the constant degree case, what we use is the Hermite normal form for the coefficient matrix of the lattice. So the HNF of the, let me write it down. So we'll use the HNF of a reduced ideal close to the one we actually want. Okay, so there's a problem. There's already a problem with e to the t. E to the t is doubly exponentially large. So you can't just compute this. It doesn't make sense. And furthermore, this ideal may or may not have a polynomial representation size. But there is a finite set of what are called reduced ideals. You basically just cut off the, if the representation size gets too big, you just say, okay, it's not reduced. And they fill out space fairly well. So given any ideal, you can pick a reduced ideal that's close by. And then you can write down the H and F for that. And the H and F is a unique representation of the ideal. And we need this unique representation because we need this constant on cosets. The only way you can get this periodicity is to have unique representations of everything. So that's just, I can answer more questions. I wasn't going to say more about this. Right now, we're working on the n-dimensional case, and we're using a different representation. So in the n-dimensional case, what we're doing is we're actually computing some approximate basis for this, like an LLL reduced basis for an approximate, everything's very approximated. And then we use a quantum representation to represent that. Because first of all, if you just have a basis for a lattice over R to the n, it's not unique, right? An LLL reduced basis. Furthermore, we have to round off everything because everything's an R to the n, so that creates another problem. But we need this unique representation. So basically what we do is we split up into a superposition over lattice points and put Gaussians around the points to handle the rounding and stuff. So that's something we're working on, and it's not done yet. But we're changing the function to be a quantum function, so we use a quantum representation. So instead of, like the examples I was showing you, these were classical functions returning classical objects. Now we have a function that returns quantum states. All right, are there any questions about that? The next thing I was going to do is try and say a little bit about how the algorithm works. Any questions about the problems that reduce to the hidden subgroup problem? Okay, so I'm going to try a little bit of an experiment and try and say very little and see if people are happy or not. But one of the reasons I'm doing that actually is because I want to show you where lattices come. This is going to be another example. We're going to see where lattices come up. So I want to do it in high dimension and just say a couple things, and then you'll see where the lattices are. Okay, so we want to think about how the quantum algorithm works for the hidden subgroup problem. And we're talking about the abelian case, since that's the case where we know that there is one in most cases. So let's think about the hidden subgroup problem over z to the n. So we're given this function, and then the hidden subgroup is going to be just some, a lattice, say. It's a lattice L in the group. Okay. So I'll write down the algorithm as two steps, and we'll ignore all kinds of details about how it works. Maybe I should move to the left here, just in case I need to leave this on the board. Okay, so the first step of the algorithm creates what we call coset states. So it's going to create a superposition over a random coset of L. Okay, so in pictures we'll just think about this. So a superposition is a complex valued vector, and it has norm 1. So we can just draw that vector down and think about it like that for now. Okay, so we'll draw what the support of the vector is, what the support of the superposition is. So there's this random vector v, and we're supported on a coset, on this coset of L. So here's v, and then we need to draw the lattice points. So whatever the lattice looks like. So our superposition is on these points here. And we can create this using the function. We evaluate the function in superposition, we measure the function value. I can say more about how that works if people want to hear about it. Okay, so this is the set V plus L. And then the second step is we compute the quantum Fourier transform of this and we measure the result. So what happens when we compute the Fourier transform over a lattice, or a coset of a lattice, so here's the quantum Fourier transform, is we end up with a superposition that's concentrated on the dual lattice. So whatever the dual lattice looks like, that's where we are. And what happens when you measure a superposition is you get a random element in your support with some probability. And so we would measure, what would happen is you'd measure a random element of the dual lattice. Okay? So this is the quantum piece. And so to get L, so our goal is to figure out what that lattice is, we would repeat this probably many times until we have a basis, so that we have a basis for the dual lattice. And then from the dual lattice, we compute the lattice. And that's the algorithm. Starting point, so you're given the function. Using the function, you create a superposition on a random coset of the lattice. Yeah, yeah, that's right. So we repeat Pauli n times. To get a basis of L star. And then compute L from L star. Okay, so for example, in Shor's algorithm, it's a one-dimensional lattice. So remember, we saw there's a hidden subgroup problem of the integers. And so the way his algorithm works is you have a superposition over a one-dimensional lattice, or over a coset of a periodic function. The way we usually talk about it is the periodic function. We have a coset of that periodic function. So in Shor's algorithm, you get a random offset. You have your periodic function of period r. And then you compute the Fourier transform, and then you're sitting on the dual lattice, which is like something like 1 over r times z, say. So over here we have k plus rz, and then you have this. So then we sample from here until we figure out r. So there are details for how this actually works. I mean, so when the group is finite, everything works exactly. You can actually do it exactly. This superposition is over a finite group. You compute the Fourier transform over that same finite group. You get something here you can think about as being the perp subgroup. Everything is very clean. Once you move to the integers, well, then you're on this infinite group, so you have to change your superposition to be over a finite group. So that starts introducing problems. It gets messier, because you have to work over a finite group. And then when you move to R, to the reals, then you have another source of error, because now your points are also being rounded at each point. So now you're truncating your group off, and you're rounding all your points. So the Fourier analysis gets worse. So that's one reason why actually R to the n is still open. Hopefully for not very much longer. We're working on it, but it's pretty messy. So this is hiding those types of things. So in finite groups, this picture is exact. Move to Z. You have to truncate the picture when you're working on Z. And for R, you have to also round points. To integers. That's a good question. How do you even define the hidden subgroup problem over R? We're still working on that too. So there are two possible ways you could do it. You could make your definition kind of ugly and incorporate rounding into the definition, which is what happened in the constant degree case. Or what we're doing now is we're using actually a continuous function over R, and since we're going to quantum states now, we can actually handle it that way. I mean, we don't know. We're adjusting the definition to try and get the algorithm to work. Or we're trying to get an algorithm to work. So I don't know what the final definition would be, but yeah, it's a good point. So one answer is use quantum states in your range, and then you can get farther. Yeah. Yeah.
So just to make it complete example, so say you have there is a lattice that you don't know, and you have some oracle that tells you how far you are from the lattice. In the phone, the distance of the phone. Okay. This function is constant on lattice cover. So you're still at the same distance.
Yeah.
So using this, you can recover the lattice.
Sounds like, yeah, if I understand the problem right.
Yeah.
If I understand what you're saying, yeah.
Yeah, so this is now again.
Oh, I see. Yeah, it would be distinct on cosets because you'd have some like spheres going around each one or something, but that might still be okay.
No, but anyway, so this one can also be called flat.
Okay.
What is not known to be called flat is what if I give an approximate distance oracle that given a bracket function space to an approximation to the distance, maybe even good one, an approximation within a factor of 2. And you see that something that's incompatible with the quantum technique or something that could be useful.
So it sounds, that's not just like a noisy version, right? That's actually somehow worse, what you're describing. So in one dimension, we have results for like what happens when it's many to one on the period, or what happens when it's maybe noisy in some ways. You know, you can tolerate some, but what you're talking about sounds like you can have some arbitrary.
Yeah, it could be adversarial.
Yeah, that sounds worse on the face of it, but I don't know. Yeah, it'd be interesting to think about. Other questions? Okay, so there are two options. One option is I can give you a little more. Well, actually, there aren't that many options. Okay. Okay. In 5 minutes, there aren't too many options, unfortunately. Well, okay, so what I would like, one thing people are interested in is this, these two approaches to quantum, finding a quantum algorithm. I can try, okay, so I was gonna maybe spend a little bit of time just saying what a superposition is and what a measurement is to make, so this would make more sense, and also what I say after it will make more sense. But with 5 minutes, that would take up to 5 minutes, so should I jump ahead and just do the, yeah. I'm going to talk about two approaches to trying to solve lattice problems with a quantum algorithm. The problem is there's quantum there, so without telling you what the model is, it's a little bit difficult. But let's see. So people, I think, are very interested in. Let me talk about this connection between the unique shortest vector problem and the sub-exponential time algorithm. So the connection between the unique shortest vector and hidden subgroup problem over the dihedral group. Okay. So first I'll tell you how you get to the dihedral group from here to here. Well, that's the main thing I have to tell you. Okay, so the setup is we're given a lattice and it has a unique shortest vector. So you have some short vector, you have multiples of it, and then the next closest vector is outside, it's much farther away. So you say you have copies of this. Okay. And we're trying to figure out what that shortest vector is in this case. Right? So this distance is much smaller than the next closest non-parallel vector. And the way, there's this approach from Regev's, one of Regev's papers, that what you try and do is create a state that's concentrated on a coset of an order 2 subgroup in the dihedral group. So the dihedral group has elements, it's a semi-direct product of Zn and Z2, so we might write down elements as like I and then a bit. And an order 2 subgroup would contain the identity plus some other element S. Okay. So we'd like to set up something that looks, where the hidden subgroup looks like that. And the idea is that, so this is where the lack of quantum is going to be a trouble, but if you imagine splitting up space into boxes, okay, we can define a function that just labels, that given a point in space labels what box you're in. Okay, so suppose you split up into a superposition over lattice points, and then you ask what box you're in. So here's the shortest vector, it's U, and we just label these, doesn't matter how, just so that they're different values. So f of a lattice point says the name of the box. And then to create the state, what you do is split up into lattice points, a superposition over lattice points, and in the second register, you put the name of the box. Okay. Now, when you measure a quantum state and you see a value, your state collapses to whatever state is consistent with that. So when you measure this, you'll see some box name, and you'll collapse to a superposition of the points. So suppose you measured a 4, then you'd collapse to these 2 points here, because there are 2 points in 4. Okay, so you get something like x plus u. Suppose this thing is called x here, and then this is x plus u. You'd collapse to a superposition of these 2 points. Now, this is not yet an instance of the dihedral hidden subgroup problem, because we need somehow to say whether the reflection is there, and this isn't doing that. And there's some technical way to fix that. So once you fix that, then it looks more like a coset in the dihedral hidden subgroup problem. Okay, so I'm not going to talk about how to do that, but there's a way to do that. Okay. So if you could just do this, and then you compute the hidden subgroup, you'd have the shortest vector, right? Is that okay? So the problem is this is a very noisy process, or it's a noisy process anyway. Okay, so what you want, like the ideal case is that every box you have has 2 points going through it and no other points inside. But what you actually get when you just split the space up into boxes is you can get other cases. So you might have a case where you only have 1 lattice point in there, and then you'd collapse just to that. So you wouldn't get a superposition of 2, you'd just get a single thing. Or you might have more. Right? You might have a case where somehow 3 points are going through. In this case, you'd collapse to a superposition of x plus u plus x plus 2u. So these things create noise. And the Kuperberg sub-exponential time algorithm starts by generating a sub-exponential time list of coset states like this. So if a bunch of them are noisy, the algorithm doesn't work.